Yeah, hi, I'm Drew Friedrichs. Try not to stay in the light as well. Today I'm going to talk about some of the research I've been doing in and around Antarctica. The title of my talk is How the Thawing of Antarctica Affects the Transport of Heat Throughout the Ocean. And then in essence, what I'll be talking about is how the melting of the continent, or thawing, is introducing a lot of new water into the coastal ocean around Antarctica, which has consequences for how heat is transported in the ocean. I have a clicker in my pocket. Go forward and backwards. Perfect. This, as is the case with all polar work, is an incredibly collaborative effort. I've been working alongside teams from 5 countries, 9 universities, and these are just the people that really have considerable official contributions to this project. The list of people who have had their hands on this at some point is just absolutely endless. Big thank you to the Korea Polar Research Institute, which have provided a lot of funding and a lot of the logistical support for this research, and all other people listed here. Just a little bit about me, as anything other than what Alex said. I'm an East Coast guy. I grew up in Virginia. I went to college in Vermont. My background is in physics, so I'm always thinking about the bare essence of movement of water and things like that. But in my time at Davis, through a master's degree and a PhD, I've been focused on environmental fluid mechanics. So how this physics, these lessons I've learned in physics, can be applied to how water moves in the natural environment. And my dissertation specifically was focused on the research we did in Antarctica and the lessons we learned about how the ocean moves down there. But in the meantime, I've had my hand in a lot of other projects around the state of California that are close to home that do mean a lot to me as well. I'm still a research affiliate for TERC, where I am heavily involved in a project up at Lake Shasta, where we're measuring temperature as it passes through the dam and supplies cold enough water for the salmon. But today's Antarctica, so I'm guessing a decent amount of you in the room have some idea of Antarctica, but I'm going to start from the basics. Here's a map of Antarctica. It's really large. It's 1.5 times the US in size, basically the US plus Mexico there. You can see the state of California. And it's almost entirely covered in ice. The average ice thickness for the whole continent everywhere is around 1.5 miles thick, but it gets up to 3 miles thick. And that ice is so thick and so heavy that it actually compresses the continent. So a lot of the land is actually below sea level. And that's a problem that I'll get into in a little bit. I've highlighted some important features that will come up here later. Let's start. There's the South Pole, not exactly in the center. This isn't the magnetic South Pole. It's the location of the South Pole. It's a station there. There's some bays. Actually, they're big, so there's seas around the edges of around the edges of Antarctica. So the Ross Sea, a really famous sea, one of the first ones ever explored, because it's due south of New Zealand. So all the British explorers made it from Australia to New Zealand, passing through their colonies, and ended up in this corner of the Ross Sea, kind of where the McMurdo Station is. This is a very large logistics and research base there run by the US, the largest base on Antarctica. As you travel around the continent to another site we'll talk about, the Amundsen Sea, also really famous. Also both, as you'll find out, a lot of things are named after polar explorers. The Amundsen Sea, famous for Thwaites Glacier, which has been in the news the last couple years as a doomsday glacier, a glacier that if it was to melt in entirely would really mess things up for us. And it's really large. That is the outline of the entire glacier's catchment basin, kind of the size of a state, basically, or a small country. Okay, so the reason we're talking about Antarctica often is a scary potential for sea level rise. This graph here is produced by the International Panel on Climate Change, the IPCC, a big collaborative effort from many countries and many professionals, produced in 2021. And it's a timeline of how the best guess in 2021 was for what sea level rise will do in the next couple hundred years. There's a timeline on the bottom, and as you go up in the graph, you get to higher potential sea level rises. All these lines are potential pathways to sea level rise that we think might happen. Each has a certain likelihood or a lot of uncertainty involved. And you can see they kind of cluster around 2,100 and about 100 years at about a little under a meter, maybe 2 feet of sea level rise predicted in the next century. We're right here in 2025, where we're already at about maybe a foot from the early 1900s. And it's going pretty slow. Our current sea level rise on average, so this is all the oceans combined, is about 4 millimeters per year. That's about 1 inch every 6 years. And only 10% of that is from Antarctica currently. But we expect as Antarctica to melt, that contribution will increase well above 10% and will dominate a lot of the sea level rise potentially as we go centuries in the future. This dotted line here shows a low likelihood, high impact storyline. So basically the worst case scenario, what is physically possible for the sea levels to rise if we have a lot of melting. And it goes off the graph in 2300. All the way up there, 15, 20, 25 feet, 30 feet. Actually, sea level rise greater than 15 meters cannot be ruled out with the highest emission standards. Luckily, there's been a little bit of evidence in the last couple of years pointing to that being even less likely than we thought, but it's still theoretically possible. 15 meters is about 50 feet. And that's in 2300. So if you think where we were 300 years ago, Benjamin Franklin running around the country, this is kind of that length of time. It's unfathomable to imagine 50 feet of sea level rise. If you're just curious as a thought experiment, what would happen if you melted all the ice in Antarctica? That would put us at about 60 meters. If you add Greenland in, we're up to 70 meters, which is in the 230s of feet. That's about the elevation of the road on the Golden Gate Bridge. So that's where it was at one point in Earth's history and where it could be one day if we melt all of the ice. Okay, all this ice and water enters the ocean at Antarctica's coastlines. So there's a couple of big features that happen at the coastline that we need to make sure everyone understands the names, basically. Hopefully everyone's aware of what a glacier is. They exist we find them in Alaska. Maybe we used to find them in Montana. We find them in Canada, Europe. But these ones are really, really big. When they reach the coastline, they're often a mile thick still. They reach the coastline kind of at this dotted line where they melt when they hit the ocean from below, and they thin and start to float because ice floats on water. So even though this ice still remains possibly 600 to 1,000 feet thick, it's floating, and it's called an ice shelf. It is a shelf kind of that sticks out into the ocean. So this glacier moves downslope from the center of Antarctica all the way to the coastline, and as it starts to float or starts to melt, that's what contributes to sea level rise. But this ice shelf is really important to managing that amount of sea level rise. There's a couple of things drawn here. This is a seamount coming up underneath the ice shelf and intersecting it from the bottom. That's a mountain kind of on the other side. And these land masses kind of pin the ice shelf there and make it hard for the ice shelf to move with the glacier. So we say that the ice shelf buttresses the glacier kind of like as a support leaning up against it. And so we want to be wary if these ice shelves break apart or start to melt, because that would cause the glacier to have an easier time sliding downhill into the ocean. And these glaciers, the ice shelves are melting actively. Water is pretty good at melting ice. And these indicate kind of the amount of melt that's occurring. And what you can see here is I'm trying to indicate that we actually expect more melt the farther under the ice shelf we go. There's a couple reasons for that. One that I'll get into later is sometimes the hot water is what makes it all the way down there, as opposed to the cold water. But one thing that you have to keep in mind is it's actually easier to melt water that's under a lot of pressure. The melting point of water changes as you apply a lot of pressure to it. This is such a case that in the center of Antarctica, under 3 miles of ice, you have so much pressure that it can be really hard to freeze water. And so you have some liquid water under the middle of Antarctica, buried way down there, really hard to find, whole lakes and river systems that we only knew about until recently. Okay, so one bad, scary implication of this is if we have melt at this bottom location, this is a downhill slope generally into the center of Antarctica, not into the center of Antarctica, but near the coast of Antarctica in some critical places. So what that means is as we have melt down here and we step the base of the ice shelf back, we then are even deeper with more pressure and deeper with more pressure. And it's a bit of a feedback loop potentially. And it's really hard to figure out how strong this feedback loop is, when it's going to kick off for real, whether it's unstoppable, how far will it retreat back. This whole concept is called marine ice shelf instability. And that really bad case of 15 meters or of sea level rise, that is in the case of really bad marine ice shelf instability, when they rapidly retreat inland. What's TERC's role in this research? Well, TERC, as a scientist and an engineer, I'm interested in figuring out why this is happening, how can we measure what's happening here. And TERC is really helpful for this because TERC has the instrumentation which allows us to make these measurements. This is 2 pictures. So firstly, this is our, this is an Antarctic icebreaker, a heavy icebreaker owned and operated by South Korea, the Eraon. That's why I'm thanking them. Without that, their logistical support wouldn't be possible. But this is our lab's electric glider, an underwater autonomous glider. It glides through the water column, basically. This is an autonomous powered AUV, the Gavia. And both of these are able to enter under large pieces of ice, places humans don't want to go. They're more disposable than a human. Obviously, we don't want to lose them, but they're also really helpful because they're autonomous. Time is money down there. And as we work, it's really nice to have the robots do the work for us. So in theory, we program them, set them up to run, put them in the water, they make their own decisions, collect the data, return to the surface, come back to us. And in the meantime, we're off doing other things. I think the icebreaker takes on average, or something approximately like $100,000 an hour to run or something like that. 80,000 a day, 80,000 a day, more than I make in a day. Only by a little bit. But yeah, so and it's a lot of pressure having everybody wait for you. So it's nice to have the robot do it on its own so you can go work on something else. So now I want to get into some of the actual work we've done. The first place we're visiting is the Ross Sea down here. Remember, this is kind of due south of New Zealand. And this is a satellite image of that site. All the white you see there is ice, but we have a couple different types of ice going on here. Outlined is the Nansen ice shelf, one of those floating extensions of the glacier that I mentioned. To the right is mountains covered in ice, and to the left is the ocean. And this is sea ice that kind of moves around and melts and freezes. But this is the ocean here. This is technically Terra Nova Bay. It's a bay as part of the Ross Sea, and it's named Terra Nova after a famous whaling boat that then was turned into basically an explorer ship that was sent down in around 1912 with Ross's party trying to race to the South Pole. You should look up that story. I'm not going to spoil the ending. Let's see. Here's Tahoe for scale. So we're actually, it's a pretty big site. But in the scheme of Antarctica, this is actually a pretty small site. Next door, so that's us right there. I don't know if you can make out that little stick. That's that. But this is the Ross ice shelf, which is 250 times bigger by area and the size of France. And it operates under generally the same physical phenomenon, same processes. So this is a much more approachable ice shelf to figure out what's controlling it. And we can take these lessons and extrapolate them forward and try to apply them to the much bigger ice shelves. I might as well say the thickness. This ice shelf is about 1 mile thick at the dotted line where it meets the land. And on the edges, it's about 600 feet thick. And this is what it looks like when you do research up against it. So this cliff, this ice face is somewhere on the order of 60 to 70 feet tall, sticking out of the water. And it's the tip of the iceberg. That means that ice, as it floats, 90% of it is below the water. So if you can picture another 600 feet or so of water going of ice going down below the surface there. That photo was taken somewhere right around here. Nansen ice shelf is what we call a cold ice shelf, and we call it a cold ice shelf because the water near it is very cold, really cold, -2 degrees Celsius or 28 Fahrenheit. That might be a red flag for you because it's below 32 degrees Fahrenheit, so you'd expect it to be frozen. But when you add the salt to the water, it drops the freezing point, just like why we put salt on the roads here, and it allows water to reach around -2 degrees Celsius or 28 Fahrenheit. Thus, the ice shelf is not melting very quickly in the scheme of ice shelves that are melting quickly. But that doesn't mean that this ice shelf is super stable and we're really comfortable with its existence. As evidenced by, in 2019, this is an image taken from April 2nd, 2019, where some cracks started forming, highlighted in orange here. And just a few days later, on the 7th of April, these icebergs broke off. Now remember, these are 600-foot thick pieces of ice. Together, these are 130 square kilometers, something like 2/3 the size of Tahoe kind of put together. You can just see how they pushed off there. And research after the fact has linked the stresses in the ice that cause them to crack to how thick the ice is and how in some places it's thicker than other places. That causes weaknesses in places where cracks can form. And so we went down in 2017 and 2019 to try to design an experiment to measure the ocean nearby. If we can identify the traces of meltwater from the ice shelf, we can pinpoint where that's coming from, where the ice is melting actively, where it's thinning, and maybe can hypothesize about how breakups could happen in the future. So we used that yellow submarine, the glider from the other slide, and we flew about 100 miles around the edges of the ice shelf here. We reached the bottom of the ocean 200 times over the course of a couple days. And I want to get into a little bit of the findings. Well, the main thing we identified was this black arrow. This is showing we saw basically a trail of meltwater exiting the ice shelf. And it's below the surface by a big margin, below the bottom of the ice shelf even. So that indicates that this meltwater is likely coming from somewhere down deep. That makes sense. As I said in the beginning, we kind of expect it to melt down there. But it's nice to see that in reality, that it's probably not from this part of the ice shelf, it's from down here. And so to see what the implications of a bunch of meltwater entering the ocean are, whether it hits the ice shelf ever or where it goes, we kind of track its movement out into the ocean. This is another satellite image, which we can kind of look at the sea ice here and see how we expect the currents to move. The general circulation in this area, the water goes from the top of the picture to the bottom and kind of follows the coastline in a big kind of spiral along the coastline. But this study site is really famous for its strong wind events. It has katabatic winds, which are downslope strong winds. We're talking 100-mile-an-hour winds. And when these blow off the ice shelf here, they blow over this island right under the W in wind, which, by the way, is called Inexpressible Island, named because of the inexpressibly awful weather that the people had to live through as they wintered there in 1912. So it shoves all the sea ice out into the ocean, but it also spins up the water, kind of following this kind of pattern. These are two eddies, one eddy spinning the water basically above the wind and one below in opposite directions. And what we actually did our measurements during these spinning eddies. And what we saw was that the meltwater from underneath the ice shelf coming from this melt actually spirals up in front of the ice shelf. And we hypothesized that under certain iterations of this event, this meltwater can actually interact with the edge of the ice shear. It's so cold that it actually helps refreeze some parts of the ice. So it could be a stabilizing factor, but it also can be melting in other spots. It's a bit of a complicated scenario, but tracking the meltwater here and how it interacts with the ice again has implications for the local thinning and thickening of the ice. This work was published a couple years ago, and I've been pretty happy with the number of little citations I've been getting recently, so you should consider checking this one out. Going to our second study site, here's where we were in the Ross Sea. We'll just head along the continent to the Amundsen Sea. This is due south of California. If you were to go south from right here, you end up through California, kind of exiting by Baja or by LA, and then you wouldn't hit basically a single piece of land until you ran into the Amundsen Sea, due south of us. Which then, if you can imagine, South America's over here. So if you have been or plan to go to Antarctica, you'll probably end up coming from this direction. When we sail from New Zealand, we end up coming in from this way, about 10-day journey from New Zealand, and then another 10 days to reach the Amundsen Sea. Yeah? What else sea? Yeah. Okay, so this Amundsen Sea is it's also famous more recently. It has a lineup of big ice shelves along it. Notably, Thwaites here is the one that's most famous for its potential to, it's the one I highlighted at the beginning of the talk, a large one that is rapidly melting. The land, by the way, the brown is land, the white is ice shelves. And these colors here indicate how much sea ice is in this area. So the white areas have sea ice basically year round, and the dark blue areas have virtually no sea ice. So these are called polynyas, a word that means it's basically a region, a bay free of sea ice for most of the year. So we really like them because we can sail around in them because it's a lot easier. Even though we have an icebreaker, some of this ice is so thick that we really can't even get through it, even in the middle of summer. So we try to get into these bays and we work in these bays. So we end up collecting a lot of data by the Dotson ice shelf, which is in the middle of the Amundsen Sea polynya, which is the most reliably open polynya. We really would like to get into this one by Thwaites, but it's hard to get by. This is actually a giant iceberg that had been there for 30 years. It floated away a couple years ago. That's the size of what we're dealing with here. So a bit of a bigger scale, basically the size of the entire coastline of California. Okay, as we talked about a cold water ice shelf because the water was cold. Well, the water is the hot tub water here. It's hot. It's +2. It's you think that this is only 4 degrees, but it actually causes a drastic change in the amount of melt that's occurring. Thus, these ice shelves are melting really quickly, and there's a lot of effort being spent trying to figure out how fast they're melting, where they're melting, what's going to happen in the future. So when we went in 2018, 2020 this was, deployed the glider right along the Dotson ice shelf. It did another 60 miles or so of profiles. We also did a couple hundred measurements off the side of the icebreaker. And we found, once again, meltwater coming out, but also this red line. This is a hot water layer. We located a hot water layer, 2 degrees, entering the ice shelf cavity at a specific spot, and then a meltwater coming out above it. So we can try to count these and basically figure out how much water is moving in and out. But what we also found to complicate the scenario, something that other researchers hadn't really been focusing on in the past, is this gray arrow. This is another layer of meltwater we found, which looks an awful lot in the measurements like the blue arrow. And so it's actually really easy, historically speaking, to take a measurement here, see the gray arrow and the blue arrow, add them together, and think that this ice shelf is melting twice as fast as it is. When in reality, you have to be really careful and look at the exact signature of this one versus the signature of this one. How much oxygen is in it, or how many nutrients are in it, and you can kind of tell the difference. And then you can count up we counted up the blue arrow and counted basically how much meltwater is coming from this ice shelf in the summer we were there. We found that it was 90,000 cubic feet per second when we were there. So for some context, the record for Truckee River flows is somewhere around 18,000 cubic feet per second. If you were to measure the Sacramento River as it flows by the I Street Bridge today, it's around 40,000 cubic feet per second. If you average around 50,000 cubic feet per second all year round, that would put you in the top 20 fastest moving rivers in the country. But it's kind of dwarfed by like the Mississippi at around like 400,000. But it's still, this is 90,000 cubic feet that's cubic feet per second of water exiting this ice shelf in the middle of the summer. And this is just one of those dozen ice shelves I showed, which is then even in itself just one slice of pie of the whole Antarctic coastline. So we're looking at a lot of melt. But there's more to be said. When we compare this measurement with measurements taken in previous years, we can start to build a timeline of what happens with this meltwater year in, year out. This is another timeline from 2000 to 2020. That's our measurement of around 90,000 CFS. And these are measurements with the same methods, basically, from other times that other expeditions have gone. And you can see basically what I call interannual variability, or a decadal change, basically, in the amount of meltwater happening here. When they went in 2000, there wasn't much melt coming out. When you went in 2005, there was a ton, back to a little, and back to a lot. You can also do the same measurements of the red arrow, which shows data that looks like this. It kind of matches. You have more hot water in some years, and less hot water, more hot water. So what I want you to take away from this slide is, yes, the long-term measurements, satellite-driven, show that Antarctica is losing mass year in, year out, and it is melting. But if you go to a specific site and you start measuring at your specific site, you have to make sure to zoom out in time enough to get the big picture. If you were measuring in 2005 to 2010, you might think that, oh, this is great, it's not melting anymore, we're on a good trajectory. Otherwise, if you just did 2000 to 2005, you would think that, oh man, projecting forward, we're in some trouble. So it's important to see this decadal variability and try to figure out the bigger picture storyline. So why is Amundsen Sea meltwater important? Why is everyone focusing on this so much? And how do the two sites that I just brought up connect? This is a map of Antarctica. There's our Amundsen Sea site, the second site, there's our first site. And there's a lot of arrows drawn on here. What I want you to take away is that these are connected. So down here, this is the Antarctic circumpolar current, and it moves clockwise around the continent. This is the Antarctic slope current, and it moves counterclockwise. And between those, you have a gyre of spinning water. And what happens in the Amundsen Sea doesn't stay in the Amundsen Sea. It gets moved along here towards the Ross Sea. And so we have to, if we're interested in things that are happening in the Ross Sea, we have to be careful of changes in the Amundsen Sea that might affect the Ross Sea. Okay, in order to explain what's going on and why this all matters, I need to give you a quick physics lesson. So if you're already tired, I don't know. Pay attention, there's going to be a quiz. What's density? Density is mass over volume. It's how much matter is in something, the amount of molecules, you count them up, and that's how much mass something has. And it's divided by the space that it takes up. And so what is more dense? I'm just going to give you the answers to the quiz. It's fine. What's more dense, cold water or warm water? Well, when you have cold water, the particles, when you have cold water, the particles stay closer together. They kind of don't move as fast. They hug each other for warmth. You have the same amount of water, but less volume. And so when you have, you keep that the same and make that smaller, you get a greater density. So generally, cold water is denser than warm water. And so it will sink generally. You can, I say usually for a couple of reasons. This is usually true, most common in freshwater. You can think about that in Tahoe. When you swim in the summer, it's nice and warm at the top because that water is not that dense. And as you dive down just a couple feet, you already tell that it's a bit colder. That's what this graph is showing. As you go from warm temperatures to cold temperatures, the density grows. Weird things happen in freshwater at cold temperatures. I'm not going to get into that right now because we have seawater, which has salt in it. So what's more dense, freshwater or salty water? Well, if you're home and you're making salt water for some reason, you really like salty pasta, you put a cup, imagine you put a cup of salt into a cup of water and make really salty water. You don't end up with 2 cups of water, actually. It dissolves into the water, and the volume stays about the same, but the mass changes. So you get a lot more mass for the same volume, and you end up with more dense water. So salt water is usually denser than fresh water. That's what this shows, is as you go to higher salinity, more salt, these numbers of density generally increase. But I say usually because it still depends on temperature. So the takeaway from this is, in general, and I'm going to show you there's more complications to this, but in general, we'd expect warm and fresh water over cold and salty water physically in the water column. The top will be warm and fresh, and the bottom would be cold and salty if it's nice and stable. Okay, I say all this because I want you to understand that the Ross Sea produces dense water, and I want you to know what that means. So the Ross Sea, almost year-round, through a lot of the year, produces a ton of sea ice. That's what's happening here. The sea ice is forming. And when sea ice forms, when ice forms, it doesn't want to keep all that salt from the ocean in it. You don't end up with really salty ice cubes. They're a little salty, but not really salty. And as that happens, the salt water is rejected from the ice. We call it brine rejection. So that produces really salty water, which we just learned is really dense. And so that water that's made, some places make a lot of sea ice. They're kind of sea ice factories producing sea ice, producing tons and tons of dense water. That water falls directly to the bottom of the ocean, basically, and spreads out wherever it can go, just down slopes. So some of it goes towards the ice shelf, pretty cold, so it doesn't cause a lot of melt. Some of it tumbles over the continental shelf into the open Southern Ocean. And this happens year after year after year and builds up a layer of pretty dense water, in fact, very dense water. We call it Antarctic bottom water, and it's some of the densest water anywhere in the entire planet. So what that means is it falls down the slope here and starts filling up all the deepest areas of the ocean that it comes into contact with. The next slide here. Another important aspect, like that, I'm going to do that again so you're ready for it. So I'm ready for it. What this does is when you have this plummeting dense water, it kind of builds a high pressure system. By that, I mean, there's basically like a wall of heavy water here that's going to stop anything from reaching, stop other water masses from reaching the ice shelf. So somewhere nearby, you have water from the more temperate climates that moves into the coastline, but it can't make it to the Ross ice shelf because of this. So this action not only creates bottom water that spreads around a lot of the continent, a lot of the world even, it stops the warm water from reaching many of the ice shelves. And here's the proof in the pudding of this dense water spreading around. This is the deep water I've been talking about. It's the blue colors. Here's our star for where we were talking about it being made. That's that spiral. It goes from the surface to the bottom, from red surface water to the bottom blue water. And then it spreads. It goes into the Pacific Ocean, goes up into the Indian Ocean, a little bit of it goes into the Atlantic Ocean, but it carries with it whatever was in it when it formed. And so it formed rapidly at the surface and dove down. So it has a lot of things from the atmosphere in it. It has oxygen in it. Has a lot of carbon dioxide in it. It has some traces of nutrients from the continent that weren't, it dove down so fast, the plankton weren't able to eat it. So it's got nitrogen in it, et cetera. And when it enters the deepest part of the ocean, It stays there for a long time, hundreds of years to thousands of years. It's buried at the bottom of the ocean here. So yes, it's moving around, but it's also kind of a sink where we can hide away things. So we really like this application for thinking about how we can remove carbon dioxide from the atmosphere. This is a major carbon sink. I think about a third of all of the Earth's carbon dioxide emissions are hidden away in water, just like this. So we want to be careful of keeping an eye on whatever is potentially changing the formation of this bottom water, because it has consequences for the water masses that spread around the continent and around the world. So what happens if we add meltwater from the Amundsen Sea? We just showed that with arrows in a couple slides ago that the continent is kind of connected from end to end. And so meltwater from the Amundsen Sea does make it to the Ross Sea. And what happens if we think about what happens when there's a ton of meltwater in a potential future? So if we add a big layer of meltwater near the Ross Sea, and we try to do that same process we did a couple slides ago, where we have sea ice, brine rejection, dense water dropping down. Well, now our water is stratified, meaning it's not really easy for this dense water to make it all the way to the bottom. Instead, it's kind of absorbed and mixed into the meltwater, and you end up with no deep water formation in the worst case. And so not only does that mess with our global circulation and all our nutrients being transported from Antarctica around the world, our carbon sequestration, hiding the carbon in the deep ocean water, but it also now allows this warm water to make it all the way to the coast of Antarctica. So, and start melting the Ross ice shelf and changing it from a cold water ice shelf of -2 degrees to a hot water ice shelf of +2 degrees. So this is something we're a little worried about, but it has a ton of uncertainty. And the main takeaway is we really need to figure out, is this possible? And if we bring a lot of meltwater over here in a hypothetical future, does this happen? Does it really stop the dropping of dense water down to the bottom of the ocean? So how can we predict if and when this happens? Well, we can't take measurements of the future. So instead, we design models. We basically build tons of equations that do the best job we can find of actually representing what physically happens in the water. The outputs kind of look like this, where we can then put in a hypothetical amount of meltwater coming out of the Amundsen Sea, and we can run the model and watch it play out and see how much of it makes it to the Ross Sea. That's ROMS, R-O-M-S. This is finite element sea ice ocean model, FISOM. They all have great names, but they tell a lot of the same stories, that we have water going from the Amundsen Sea to the Ross Sea. But they're not perfect. Modeling ocean mixing is hard for a lot of reasons, but the reason that I like to talk about is because the ocean is turbulent. And turbulence is a scary word, even for me. And what that means, basically, if you've been on a plane and you experience turbulence, is the water or the air is really bumpy. It's actually mixing really rapidly, and it's hard to drive smoothly through it. The air is trying to mix your plane, basically. And this happens, actually, at many scales. But turbulence often mixes heat and salt, which is relevant for figuring out how quickly the brine rejection will mix into the meltwater at really small scales, like really small centimeter scales. And models just really can't be built at centimeter scale covering the entire ocean. So what they do instead is they do something called parameterization, where they make simpler equations which end up with what they think is the same product, but in a simplified sense. So in the meantime, they make approximations and assumptions, these models do. And we can test those assumptions by actually measuring those tiny little scales in turbulence, those little centimeter mixing things. And we do that with our robots and profilers. This is the glider, and on top of that is a microstructure turbulence profiler. Here's one in my hand here, not effects to a glider. Basically, these measure tiny, tiny changes that are resulting from these little turbulent mixing events. I'm talking like a 1,000th of a degree Celsius, or what's the difference between the flow at this millimeter, how fast is it going at this millimeter versus that millimeter, things like that. Things that a model doesn't really have a realistic chance at measuring or modeling for the entire ocean. So what they are good at is simple cases. Our simple case of warm and fresh over cold and salty. I want to run through a little thought experiment here. So if we take a particle of water and try to mix it in this environment, and by mix it, I mean introduce some sort of wave or energy that forces that warm and fresh. Remember, it's less dense because it's warm and fresh. We force it down. Think of like in the water, you take a ping pong ball and you shove it down in the water. It's going to want to bounce back up and bob around. But in the meantime, it changes temperature before it bounces back up. So when it bounces back up, it's a little bit colder, so it doesn't quite go as far. It's then still bobbing back and forth, and but it warms up before it can go back down. So it, again, doesn't quite go as far, and again, doesn't quite go as far. So what I want you to take away from this is our understanding of how this happens here is we take a lot of energy, dump it into the system, and this particle of water only kind of moves this way because this water column wants to be this way. It has warm and fresh above cold and salty. So water doesn't mix super efficiently. In fact, we apply coefficients of 17% mixing efficiency. So as we dump a lot of energy into mixing water, only 17% of it actually physically mixes the water. That's fine and dandy when it's warm and fresh above cold and salty. The models do a pretty good job, and that works on a big scale. When you start talking about really weird Antarctica situations, this might not apply anymore. Let's clear the whiteboard and flip it. So in the Amundsen Sea, we still have fresh and salty, but we actually have cold and fresh and warm and salty. This is weird. It's still okay because salty water is often denser than fresh water. It really drives the density. And I had that little usually mark, so warm water is only usually less dense than cold water. But in this circumstance, let's try the thought experiment again. So we take our ping pong ball of water and we shove it down in the water column, and it changes temperature, but this time it heats up. And as we heat up, because the water's warm, and as we heat up warm water, if it stays the same in salinity and you just heat it up a little bit, it becomes less dense instead of more dense. So when it shoots back up to the surface, it goes farther than it was the first time. And then it wants to keep bobbing, but it cools down because it reaches this really cold water up here. And then it overshoots again. And so basically what's happening here is we're not applying that much energy, maybe the same amount of energy, but it's mixing in greater amounts. This is called double diffusive convection. It's a really complicated concept. I can explain what those words mean later, but basically in essence, in these scenarios, you might put energy into the system, but it mixes more easily than 17%, something like 50%. And because this is generally rare in the ocean, most circulation models don't really take it into consideration. They believe that, yeah, it might be possible, but it doesn't really happen. We can kind of turn that off or not really consider it. But we're finding in our measurements of Antarctica that we need to consider things like this. Let's show some real data. Firstly, let's show some data that maybe you're familiar with. This is a profile of Lake Tahoe. It's what scientists at TERC and the staff collect all the time, every month. This is from December 31st, 2023 or something like that. So we have relatively warm water at the top, 7.5 degrees Celsius, which is like in the 40s. And as you swim down, depth, I have feet and meters marked here. Swim down maybe 100 feet or something, it starts getting really cold. And then it stays cold as you go to the bottom of the lake. It's a pretty simple case. Doesn't really have salinity, but it's cold above warm. Now here's what it looks like in Antarctica. It's to the same scale, but I've moved the temperature bar, but it's still 4 degrees difference. So we start at the surface, it's warming up from the sun, it's a little warm. As we go down, it gets cold, but then it gets warm again, then cold again, then warm again, then cold again, warm, cold, really warm. Obviously, this is a bit more complicated. And we do have that warm, salty, under fresh and cool. This little bit right here helps us prove that what we were getting on that last slide, that spiraling mixing is occurring, because when it happens over and over again for a long time, it develops these weird formations in the temperature profile. There's more of them heading down here. So this is basically saying that this water is mixing probably more efficiently than the models are thinking. And this is relatively easier to understand compared to this. I mean, this doesn't show these classical staircase events. We see like a step there, but then like an inverted step there, and then another step, and then, boy. The point is, it's really complicated, and these assumptions, which might work across the whole ocean, fall apart when you're specifically interested in figuring out what's happening here and here. And why are we specifically figuring out what's happening here and here? Because this is where the meltwater is. I'm going to throw another graph up. Instead of temperature on the going across, this one shows the amount of meltwater in the ocean. So at each measurement, we have a number between 0 and 6. This is in percent. So at this location right here, this is at 500 meters, we have a sample that has 5% meltwater. That's of the entire sample, 5% of that entire sample came specifically from the ice, not from the ocean somewhere else. And then it's 0 here and back up to 5% there. But these locations correlate with our strange physical phenomena that are underappreciated. So what I want to say here is that basically our measurements are showing that models that want to predict how meltwater from the Amundsen Sea moves to the Ross Sea, affects the deep water formation, and that changes the global circulation patterns, might depend on the tiny, tiny physics that happens at these little interfaces, which we can measure, but the models don't really appreciate yet. Okay. Summary, starting from the beginning. We started with the glaciers contributing to sea level rise, but we were interested in keeping an eye on those ice shelves that are buttressing the glaciers, but those ice shelves are melting from below with warm water and even with a little bit of colder water. And TERC is specifically able to take measurements, direct measurements using our robots in and around these ice shelves. So we board our Antarctic research icebreaker, head down there, drop the robots over the side, they swim around, collect them, bring them home back to TERC, analyze them. And what we're helping is we're helping figure out oceanographers where their assumptions about how water mixes, where they fall apart. And that's near those little ice meltwater layers. And so we find, us and the modelers find that meltwater is incorporated into the formation of dense bottom water in the Ross Sea, even meltwater from 1,000 miles away in the Amazon Sea, which is rapidly melting. So we're worried that in the future, with more meltwater coming in from the Amazon Sea, that it will have an effect, a real effect on changing the formation of deep water, the spread of deep water around the oceans, and the change of basically global climate circulation. How much heat is transported thousands of miles away into the Pacific Ocean, into the Indian Ocean, the nutrients, the carbon, etc. Okay, so with that, I hope you learned something today. I hope you didn't fall asleep in my density lesson. I hope you enjoyed some pretty pictures of ice. And I want to thank you for coming out today through the snow. I want to thank all my collaborators. I want to thank everyone at TERC, because even though these measurements are happening in Antarctica at the bottom of the world, we do all the testing here in Lake Tahoe. Lake Tahoe is like a perfect testing day. It's perfectly clean water. We don't have to worry about the damaging the effects of salt. We have a lab right on the water, makes things easy. We have an incredibly talented staff to support us as students. And this kind of research couldn't happen without everybody involved at TERC. So thank you. Yeah. Depending on where you go. Let's fall back in the beginning. That's fine. Sorry. Okay, yeah, let's go back into a slide here and look. So, yeah, it's a great question. All right, so the question I think is a little bit more information on how deep and thick everything is, basically. How deep is the ice? How deep is the ocean there? Are we measuring to the bottom? Things like that. So let's do, are you okay working off of this slide? Yeah, so this red profile is in the Amazon Sea near the Dotson ice shelf. If you go past if you basically walk on top of the ice shelf inland, the ice shelf at the edge is 600 feet thick, and it grows. And by the time you have all ice all the way to the seafloor, it's a mile thick. And if you keep walking, it goes to 2 miles, 3 miles eventually. And so at the edge, where the ice shelf is, it's about 600 feet. So it correlates to somewhere around there in the profile. This down here at 800 feet, sorry, 2,500 feet is the bottom of the ocean. So these profiles go to the bottom of the ocean there. And in the scheme of things, this is actually not that deep. This is on the continental shelf, so as you drop off it, you lose another thousands and thousands of more feet. Does that help? So the meltwater is the whole thing. Yeah, so there's meltwater almost everywhere. There's some spots where there's very little, and for reasons that I don't need to go into, but I'm happy to go into. We don't measure the surface. But there's 2 big layers of meltwater, the gray one that doesn't come from Dotson, and the blue one that comes from Dotson. And we tell them apart. We count up this one. We found it was 90,000 feet per second. Sorry, 90,000 cubic feet per second. Yeah.
You mentioned that the bottom water.
Yeah. Okay, so the question is, the first comment is correctly that this deep water that's produced on the coast of Antarctica that plummets down is a carbon sink. Carbon from the atmosphere enters that water and is sunk down to the bottom of the ocean. So the question was, what happens when we increase CO2 in the atmosphere? Unfortunately, I'm not the perfect person to talk to about that. There are people in this audience that can answer better questions about this. But so I don't know exactly what's going to happen, to be fair. It is something that a lot of people are putting a lot of effort into. figuring out how we can design the surface of the water, how we can alter it to absorb more carbon. We don't want it to reach a point where it can't absorb anymore. I know it depends on temperature. So as you change the temperature, it changes the ability to absorb carbon dioxide from the atmosphere. But going forward, my knowledge stops at carbon dioxide allowing the air temperatures to heat up, which heats up the water, which brings warmer water to Antarctica. That's kind of my knowledge, and less of how the carbon dioxide enters the water, unfortunately. Sorry. Yeah. Great question. Yeah. So the question is, how do we characterize this water? How did I get from these profiles of temperature to that profile of how much meltwater is in it? So I measure several ways to do it. I do it the way that I find the easiest, which is also the least precise, and that's by measuring temperature, salinity, and oxygen. And then we know we have basically 3 knowns, and we have 3 waters that it could be. It could be meltwater, it could be cold water, it could be warm deep water. And so we can make a system of equations and solve them for how much % of each water mass is in it based on but it's more complicated than that because these characteristic values of what do we expect pure meltwater to be changes. Actually, it's pretty constant because the ice is so old, but the water that's from the deep water changes year to year. It's a little bit more salty this year. And so we have to be really careful about whether we're using the right values to calculate that. The people who do it more precisely do chemical analyses of the water. They do the same end members, but they do it with much more precise chemical samples that don't change as frequently as my temperature and salinity do, but it's much more expensive, and you only end up with 6 data points, as opposed to I end up with thousands and thousands of data points, and I can collect a profile every hour, and it processes itself, and I get the data back. The best studies have them both. Yeah.
Let me preface my question.
You'd be surprised.
Some numbers about projected sea level rise.
Mhm.
My question is,
Yeah.
Those numbers include those other places, or was that just Antarctica?
By the way, that was a totally fine question. I don't know. You don't need to undersell yourself. That is something that is very. So the question was, in the beginning, I showed sea level rise projections, and those are the best guess of everything combined. Not just melt from Antarctica, not just melt from Greenland, but weird things like warm water physically expanding and getting bigger, stuff like that. Coastlines raising or lowering in the water column. Lots of weird stuff happening. Currently, as I mentioned before, it's important to note that Antarctica is not the major contributor. It's only 10% of modern day sea level rise. But the scary thing is when we look in the future, if we have an Antarctica that melts fast, we'll quickly grow past that 10%. In fact, Greenland is more important right now if we want to figure out what's contributing to sea level rise today. Greenland is melting faster than Antarctica, but we'll run out of Greenland ice that's melting faster than we run out of Antarctica ice. Does that help? Yeah. Yeah. Mm-hmm. Yeah, it might be misleading. Yeah. Mm-hmm. Okay, so this was a comment about. I'm gonna fly back. Sorry, online Zoom moderator. This was a question about this data set here. What's causing this year-over-year change? And it's complicated. And we're figuring it out still. It has to do with big atmospheric circulation, like tied into El Nino, La Nina. Are you familiar with the concept? So you have these years that are wet due to large Earth-wide circulation patterns that bring warm air, cold air down. That does affect Antarctica, but we also have our own regional decadal circulation down there that interacts with El Nino. And so I think the idea is that El Nino and this southern version of El Nino interact with each other, which affect the amount of sea ice that allows heat to enter the atmosphere. If you have no sea ice, you can get more heat from the atmosphere in. You can also, when the wind blows on open ocean, it can move the surface currents away, which bring up deep water and things like that. And so it starts at the global scale with huge circulation, atmospheric wind patterns, basically, changing the local weather here on a decadal scale, which then translates into the ocean, moves the ocean, and allows the warm water to behave differently, which changes the way the meltwater is produced. I personally haven't. No, I'm not going to go that far. My contribution was stating that we are indeed seeing a second peak. So before this study, we didn't have that one. And the published papers were, look, it went up and it went down. And now we can say it's going back up. But yeah, I guess my prediction is hang on for a couple of years, it'll go back down again, it'll go back up again. But I promise you, buried in here is long-term change if you keep zooming out farther. Yeah, please hit me. Yep, sure. Mm-hmm. Mm-hmm. Yeah, sure. Mm-hmm. Mm-hmm. Yeah, I don't know super specific. So, okay, so the question was, we talked about density. We talked about warm and salty water being different densities, but can you make the same comments about ice, basically? Is that kind of the question? To me, ice is so light. So what's happening here is in fresh water, the water is becoming denser as we get colder. And then as it becomes extremely cold, it becomes less dense again. And that's why ice floats, basically. Yeah, it's super unique. And we'd be in some real trouble if that didn't happen and all of our ice sunk to the bottom of the ocean. Yeah, and so, no, I don't really know how, to be honest, how salty the ice is, especially the sea ice. I can tell you that my N member for ice shelf ice in my calculation for, instead of isotopes, I use temperature and salinity to figure out how much meltwater is in. I assume that water has no salinity in it. That's ice when it melts. It's purely fresh. It's that graph up there. But it quickly gets mixed into this graph. But yeah, but it gets more complicated when you have sea ice. Any other questions about life in Antarctica? Yeah. Yeah, the little balls of water moving up and down. Uh-oh. All right. Yeah. Oh, you meant the blue line. Yeah, the decadal change. No, sorry. Mm-hmm. Yeah. So the question is, how does this pattern reconcile with the fact that I started this talk by saying that Antarctica is losing mass year over year? And this would suggest that, I don't know, it loses mass this year, but it doesn't really lose mass the next year. It's a great question, a really valid question. I think this is just one local site that doesn't completely control the whole situation. Although it is a really important site. I was just looking at an updated graph. It's really easy to find. If you just Google like Antarctic mass loss. By the way, the net loss of it changes each year. It obviously refreezes in the winter and melts in the summer, but that summation comes out at 150 billion metric tons of meltwater a year, which doesn't mean anything to me, but that is, in numbers are hard, but that's the same volume of Lake Tahoe. So it fills up Lake Tahoe with net meltwater every single year. Sometimes it's 130, sometimes it's 200 or something, but it doesn't immediately match up to this. You're right. So it's a much more complicated scenario. I guess I'll explain it away by saying that this is one Dotson ice shelf in the Amazon Sea, which is just one piece of the pie, although it's a really important piece. I wouldn't be surprised if you could see this signal in that data set, but from the bird's eye view of looking at 30 years of Antarctic mass loss, which is from satellites measuring how much ice there is there, you're right, you can't see that by immediately. So, sorry for the not great answer there. Yeah. Yeah. Yes, I think so. Yeah, we've been doing pretty high intensity satellite measurements since around 2000. I'm not sure the best gravity based things were around in 2000. I think Alex might know a little bit better about that. Maybe I don't. But yeah, the satellite based estimates go back to about this time when we were first breaking through that. I mean, these were the first icebreakers to break through that ice and really make reliable, rigorous scientific profiles that can be compared in quality today. Qualitative measurements go back to 1912 when we walked to the South Pole and picked up fossils and things. And you have, yeah, and you really, when you look back at the review papers that talk about all of the measurements in the Amundsen Sea, I mean, people were measuring it decades and decades ago. And we do have imagery from decades and decades ago. I think in the 40s and 50s, we did a lot of flyovers of Antarctica and took images, which we can use somehow to figure out how high the elevation was. But these days we use really precise altimetry, meaning basically the distance from an instrument to the surface of the ice. And we know where that instrument is so clearly, whether it's on an airplane or a satellite, that we can figure out year in, year out, whether that ice is then growing in the summer and shrinking in the winter. And we can also use gravity. We can figure out there's more mass this year than the previous year. And yeah, in my experience, it lines up pretty well. Yeah. I'm sure there must be. And yeah. I'm sure there must be, but I'm not that I'm super knowledgeable. I mean, yeah. Kenny or Alex, do you know anything about isostatic rebound in Antarctica?
Basically, he's looking at satellite measurements to speed of the glaciers, and he's showing the speed of the glaciers that are accelerating because they're losing the pressure. So he has some in his paper about his talking about the rebound as well, and how that correlates, how the speed of the glaciers correlates.
So yeah, so the question was, do we have any information on isostatic rebound, which is the growing back up of the plate? Basically, I said that the Earth down there is compacted by the weight of the ice. So when you remove the ice, the Earth kind of expands back again. And we're seeing that in North America, the retreat of the ice sheet up here. And so yes, it's happening and people know about it and can measure it. It just doesn't affect the fluid mechanics that I'm looking at directly enough for me to be super knowledgeable about it. I recommend going to Antarctica. Thanks.